Hello, everyone, and welcome to today's presentation. I'm excited to have you here as we explore some fundamental concepts in machine learning. The title of our talk is Foundations, Feature Representation, and Practical Applications in Machine Learning. We'll be diving into how generative models and naive Bayes are used for text classification. Over the next few slides, I'll guide you through key ideas, practical insights, and real-world applications. So let's get started. Today, we're diving into how generative models and naive Bayes play a crucial role in text classification. Naive Bayes is actually a classic algorithm that falls under the category of generative models. It's widely used for classifying text, like sorting emails into spam or not spam. We'll look into how it's derived and how it's practically applied to solve real-world classification problems. Generative models, in general, are powerful because they can be applied in various areas such as spam filtering, fraud detection, and even medical record classification. For this lecture, though, our focus is on their application in text classification tasks, which is a common and important use case. So, what exactly are generative models? They are machine learning algorithms that try to understand how data is created or generated. By modeling this process, they can help us classify new data points by estimating the joint distribution of inputs, like words or features, and their associated labels. This understanding is key because it allows us to see how generative models, including naive Bayes, can effectively distinguish between different categories based on how the data was generated in the first place. Let's take a closer look at the challenges and datasets involved in text classification. The 20 Newsgroups dataset is a great example here because it really highlights some of the key difficulties we face. It's also a widely recognized benchmark, meaning it's used to test and compare the performance of different algorithms in this field. When it comes to benchmarking, the dataset is typically split into training and testing sets based on the posting dates. This method helps ensure that we evaluate our models on data that they haven't seen before, which is crucial for assessing their real-world effectiveness. Now, the dataset itself contains about 18,000 posts, and these are evenly spread across 20 different topics. These topics cover a broad range: medicine, computer graphics, religion, and more, showing just how diverse the categories can be in text classification tasks. One of the big challenges in this area is the high dimensionality of text data. The number of features or dimensions is proportional to the size of the vocabulary, which can be enormous. This makes it necessary to develop specialized feature representations that can handle this complexity efficiently. Finally, let's talk about the nature of the data itself. Unlike fixed-length vectors, text documents are sequences of words with variable length. This variability introduces unique challenges because many algorithms expect inputs of a consistent size, so we need to adapt our methods accordingly. Understanding these aspects is essential as we explore different models, like generative models and naive Bayes, which are often used to tackle these challenges in text classification. Now, let's talk about feature representation for text, which is a crucial step in building effective text classification models. One of the most fundamental approaches is the bag of words model. This method represents each document as a vector that indicates whether specific words are present or absent. It's a simple yet powerful way to turn unstructured text into structured data that machine learning algorithms can understand. In addition to just noting presence or absence, we also look at word occurrence counts. These can be binary, simply indicating if a word appears, or they can be frequency counts, showing how many times each word appears in the document. This helps quantify the textual data, making it easier for models to learn patterns. Another important aspect is handcrafted features. These involve selecting specific words or indicators that are relevant to the domain or task. For example, if you're classifying medical documents, certain keywords might be particularly meaningful. Handcrafted features allow us to tailor the representation to capture specific nuances of the text. Finally, transforming raw text into meaningful features is a vital step. Without proper transformation, raw text is just noise. By extracting relevant features, we enable our models to recognize important patterns and make accurate classifications. This process of feature transformation truly underpins effective text analysis and classification. Now, let's look at the bag of words representation and some practical considerations to keep in mind. First, techniques like stemming and stopword filtering are key practical improvements for the BOW model. They help enhance the model's performance by reducing the dimensionality and noise in the data. Stopword filtering is particularly useful because it removes common words such as the and that don't carry much meaning. Removing these words helps reduce noise and makes our representation more meaningful. Stemming, on the other hand, reduces words to their root form. For example, words like slowly and slowness both become slow. This process helps us cut down on the number of unique words we need to consider, which in turn reduces the dimensionality of our data. When we talk about bag of words, we typically have two approaches. Binary BOW and count BOW. Binary BOW simply indicates whether a word is present or not in the document, whereas count BOW records how many times each word appears. Both methods have their uses depending on what we're trying to achieve. Overall, representing text as a BOW vector allows us to convert unstructured text into a structured form that algorithms can work with. This is fundamental for many text classification tasks, especially when combined with models like Naive Bayes, which we'll explore further. Now, let's look at how we can perform classification using bag of words features. This approach tends to give us quite good classification accuracy, which is encouraging. It really shows the power of combining bag of words with discriminative classifiers like logistic regression. When we use these together, we're able to effectively distinguish between different text categories. To make this concrete, I'll show you a Python code snippet that demonstrates how to implement logistic regression with BOW features. It uses the scikit-learn library, which is a popular tool for machine learning tasks. With this, you can train the model on labeled data and then use it to predict the topics of new documents. Training logistic regression on BOW features involves a straightforward process. You first convert your text into numerical features using bag of words, and then you fit the logistic regression model to this data. Once trained, the model can predict the category of any new document based on its BOW representation. After you've featurized your text data with bag of words, you can apply standard classifiers directly. This method essentially transforms your raw text into a structured, numerical format that machine learning models can easily work with. It's a simple yet powerful way to turn unstructured text into actionable insights. Let's take a moment to review some supervised learning models. Many of these models define what we call conditional distributions, denoted as p theta, yx. This means they model the probability of a target y given an input x, which helps us understand how the model makes predictions. This probabilistic perspective is really useful because it guides us in understanding and optimizing the model's behavior. When it comes to learning the parameters of these models, we typically do so by maximizing what's called the conditional maximum likelihood. Essentially, we're trying to find the parameter values that make our observed data most probable. This approach is mathematically equivalent to minimizing something known as log loss or cross-entropy over the training data. Now, a key example of a supervised learning model is logistic regression. It models the probability that y equals 1 given as sigma of the dot product between theta and x, where sigma is the sigmoid function. This gives us a probabilistic framework for binary classification, which is really powerful. In general, supervised learning models map inputs x to targets y using parameters theta. Many of these models, like the ones we've discussed, have probabilistic interpretations. They define these conditional distributions, p theta, yx, which helps us understand not just what the prediction is, but how confident the model is in its predictions. Now let's look at the difference between discriminative and generative models. Generative models aim to model the joint distribution p, x, y, which means they specify how the features relate to the labels p, x, y, and also include the class priors p, y. This allows us to make predictions using Bayes' rule. Essentially, we calculate P(yx) proportional to P(xy) times P(y). One of the key advantages of generative models is that they can generate new data, handle missing data, and even incorporate prior knowledge into the model. However, it's important to note that in some tasks, generative models might be less accurate compared to discriminative models. On the other hand, discriminative models focus directly on modeling P(yx), which means they're designed to predict labels based on the given input features. For example, logistic regression is a classic discriminative model that outputs class probabilities given features. These models tend to deliver higher accuracy in classification tasks and are generally simpler to implement. The trade-off is that they're not designed for data generation, nor do they handle missing data as effectively. So, in summary, generative models give us a way to generate data and handle certain complexities, but might sacrifice some accuracy, while discriminative models focus purely on making the best predictions possible, often with better performance in classification tasks. Let's talk about generative models for text classification. A naive approach to modeling would require an infeasibly large number of parameters, which is not practical. That's why we need to make simplifying assumptions to make these models workable. Modeling the probability of the text given the class P, X, Y directly is really challenging because of the high dimensionality of text data. Think about the large vocabulary size. Modeling each word's contribution directly becomes computationally expensive very quickly. In generative models, we represent documents as bag-of-words vectors. Denoted as X, this means we simplify the text into numerical vectors, which makes processing much more manageable. The core idea in these models is to focus on fitting class-conditional distributions, P theta, xy equals k. For each possible class k, these distributions help us understand how likely a particular set of words is, given a class. We also incorporate priors P theta, y equals k, to estimate how probable each class is overall. Putting it all together, these models aim to learn the likelihood of the text for each class and the overall class probabilities. This way, we can predict the most probable class for a new document based on these learned distributions. Now, let's take a closer look at the naive Bayes model and why it's so popular for text classification. Surprisingly, despite its simplicity, naive Bayes performs quite well in these tasks. Its ease of implementation and computational efficiency make it a go-to choice in machine learning applications involving text. One of the key points to understand is the independence assumption. Naive Bayes assumes that the presence of one word is independent of the presence of another, given the class. While this isn't always true in real-world data, meaning the independence assumption is often violated, the model still tends to perform effectively across many scenarios. Another important aspect is how naive Bayes manages to be computationally efficient. Instead of having to estimate an exponential number of parameters based on the vocabulary size, it reduces this to a linear number. Specifically, it requires k times d parameters, where k is the number of classes and d is the vocabulary size. Instead of k times 2 to the power of d, this reduction is what makes the model scalable and practical for large datasets. When it comes to modeling each word's presence, naive Bayes uses a Bernoulli distribution with a parameter called psi jk. This essentially simplifies how we represent the probability of each word appearing in a document, making calculations straightforward. Finally, the core assumption here is the conditional independence of words given the class. Mathematically, this means the probability of a document given a class is the product of the individual probabilities of each word, conditioned on that class. This assumption, while not perfect, allows naive Bayes to efficiently estimate class probabilities and perform well in many text classification tasks. Now, let's take a closer look at how we learn the parameters in naive Bayes for text classification. The key parameters are defined mathematically as phi k equals divided by n, and psi jk equals the count of documents where equals 1, and y equals k divided by. These formulas give us a clear framework for estimating these parameters. What's really useful here is that the model's structure allows for what's called closed-form solutions. This means we can compute these estimates directly and efficiently, which simplifies the learning process quite a bit. When it comes to calculating word probabilities, psi jk, or the probability that word j appears given class k, is determined by looking at the fraction of documents in class k that contain that word. This step is crucial because it captures the relationship between specific words and their associated classes. Then, for class priors, phi k, which tells us the likelihood that a document belongs to class k, we estimate this as the proportion of documents in that class. This helps us understand how common each class is within our dataset. Altogether, these parameter estimations form the backbone of the naive Bayes model, enabling us to make predictions based on the patterns in our data efficiently and effectively. Now, let's look at how we actually make predictions with naive Bayes. After we score each class, the model then selects the class with the highest probability as the predicted class. This step is crucial because it ensures we're choosing the most likely classification based on the data we've analyzed. Moving on to the next step, we focus on selecting the most probable class. The approach here is to efficiently score each class by evaluating how likely the document belongs to each one. To make this process manageable, we use logarithmic computations. These log calculations simplify the multiplication of probabilities into addition, making the scoring more straightforward and numerically stable. Specifically, when using the Bernoulli-naive Bayes model, the prediction formula becomes a sum of log probabilities. It looks like this: the log of the prior for class K, plus the sum over all features of the feature's presence or absence and their respective log probabilities. This formula takes into account both whether a feature appears or does not appear in the document. Finally, given a new document, represented as X, we predict its class by calculating the class that maximizes the posterior probability. Essentially, we compute the probability of the document given each class, multiplied by the prior probability of that class, and pick the class with the highest value. This process ensures that we're making the most informed and statistically sound prediction based on the data. Now, let's look at a practical example of applying naive Bayes to the 20 newsgroups dataset. On this slide, we're focusing on how we estimate parameters using a simple Python code snippet. What this code does is calculate the class-specific probabilities, or likelihoods, and the priors based on our training data. By doing this, we can then predict the class of new documents with quite good accuracy. In this case, around 87% on the training set. This high accuracy showcases the effectiveness of the Bernoulli-naive Bayes model, especially when working with binary features like presence or absence of words. Next, once we've estimated these parameters, the model uses them to predict the classes of new documents. It combines the prior probabilities with the likelihoods to make these predictions, relying on the learned statistical measures. To get these estimates, we calculate the class priors and the word probabilities within each class from the training data. This involves some straightforward statistical calculations that tell us how likely a class is and how likely each word is within that class. In this example, we're applying Bernoulli-naive Bayes specifically to a subset of the 20 newsgroups, restricted to 4 categories. We start by extracting binary features using Sklern's count vectorizer, which converts our text into a binary bag-of-words format, indicating whether a word appears or not. Altogether, this process demonstrates how we move from raw text data to a model that can effectively classify documents, highlighting the power and simplicity of naive Bayes in text classification tasks. In this final slide, I want to give you a quick summary and overview of the algorithm we've been discussing. At its core, the generative models and naive Bayes for text classification rely on a key assumption, that features are independent of each other. This independence assumption makes the computations much simpler and more manageable. However, it's important to remember that in real-world data, this assumption might not always hold perfectly, which can affect the model's performance. Moving on, there are different variants of naive Bayes. such as Gaussian and multinomial naive Bayes. These variants are designed to handle different types of data beyond the basic Bernoulli distributions, making naive Bayes quite flexible for various applications. One of the biggest advantages of naive Bayes is its speed and simplicity. It's quick to train, easy to implement, and despite its simplicity, it often performs quite well in text classification tasks. That's why it's still so popular in practice. The goal of the algorithm is to maximize the log likelihood of the joint data distribution. We achieve this efficiently through closed-form maximum likelihood estimates for the parameters, which makes the training process straightforward. Specifically, Bernoulli naive Bayes is a supervised, multi-class classification method. It models the occurrence of words using Bernoulli distributions, combined with categorical class priors, to distinguish between different classes effectively. Overall, this foundation allows naive Bayes to be a powerful, fast, and practical tool for text classification, even when its assumptions don't hold perfectly in every case.